QUIC, which stands for Quick UDP Internet Connections, is a modern transport protocol that runs over UDP and it integrates TLS 1.3 for secure communication. Unlike TCP, QUIC reduces latency by combining the connection establishment and encryption into a single process. In QUIC, a connection starts with the initial packets, which carry the handshake data used to establish the encryption keys. After the handshake begins, QUIC can send the application data either through 0RTT or after the handshake completes using the 1RTT packets, which are fully encrypted payload packets. So let's observe this in Wireshark. Here we can filter out the QUIC packets by writing QUIC here. And you can see we only have the QUIC packets here. Only the QUIC packets are displayed. So here the packets which are numbered as PKN1, 2, 3. The packet numbers 1, 292 till 1294, they all are the initial packets. These packets, they carry the crypto frames used for the handshake process, and the crypto here, it can be seen. Crypto is written here. So further down, we can see the protected payload packets. These represent the 1RTT encrypted data where actual application data is being transmitted securely. But here we can also see a 0RTT packet, which allows the client to send the data even before the handshake completes. So we can see the 0RTT packet here, as I said, and this demonstrates how quick transitions from connection establishment to secure data transmission. So now let's have a look at the quick long header. The quick long header is used during the connection establishment, and it includes the fields such as the version, the destination connection ID, the source connection ID, the token and the token's length, the length of the data, the packet number, and the payload like the frames, the crypto, ACK, padding, etc. etc. And crypto is basically the TLS handshake that is integrated into the quick. Now let's verify this quick long header in the Wireshark. Here I'm opening the very first initial packet, which is named as PKN1. And here we will expand the quick IETF packet. And here when we expand this, we can see the version of the protocol that we are using. We can see the destination connection ID and the source connection ID, which identifies the connection. And we can also observe the packet number here. The packet number here is termed as 1, which we saw on the starting. And if we expand the frames, we can also see crypto frames which carry the TLS handshake data, and this confirms how the quick long header is used during the handshake phase. After the handshake completes, quick switches to the short header format. Unlike the long header, the short header consists of very few fields because the connection has already been established, and it mainly includes the destination connection ID, the packet number, and the frames, which include crypto, ACK, padding, the thing that we saw in the long header format. Let's verify the short header format of QUIC in Wireshark, and here we can see the protected payload packet, which represents the 1RTT encrypted data. We will open it and expand the QUIC protocol. The headers are here. And compared to the initial packets, there are very few header fields which are visible because most of the information is encrypted. Only the essential fields such as destination connection ID, the packet length, they only remain visible to us. Now let's move on to packet number spaces. QUIC uses separate packet number spaces for different encryption levels, including the initial, handshake, and 1RTT packets. Each space maintains its own independent sequence of the packet numbers rather than using a single global sequence. Here we can see that we have initial, handshake, and then we have the 1RTT space, and we can see here independent is written. That is, initial space packets are independent of the handshake space packets. Like if the handshake space packet is lost in the network, the initial space packet, it will definitely be reached to the destination. And this separation ensures that the acknowledgements and the loss detection in one place do not interfere with the another, as I already told. And each one of them have the packets starting from 1. Like initial space has the packets starting from 1 as well, such that these packets, they do not get confused with each other, even though they both have the name 1, but they are coming under different spaces. So that's the difference. Therefore, the three packet number spaces can be verified in the Wireshark. Here I am selecting the initial packets, the first three ones, and they are of the quick connection and they use their own packet number sequence. Now, when I move to the handshake packets, we can observe that the packet number again starts from 1, and this can be by selecting this, we get this here. So we have only one handshake packet, so it does not have any number, but at the back end, it has been identified as packet number 1. And this shows that the handshake packets are using a separate packet number space independent of the initial packets. Otherwise, it would have had a PKN as 4. And even though these packets belong to the same connection, their numbering is maintained separately based on the encryption level. Therefore, this confirms that QUIC uses independent packet number spaces, which improves the loss detection and it prevents the ambiguity during the retransmissions. Now moving on to loss detection, this diagram here, it illustrates how QUIC performs loss detection using the acknowledgement-based and the time-based mechanisms. In acknowledgement-based detection, the sender tracks which packets have been acknowledged by the receiver. And if a packet is not acknowledged, but packets with higher packet numbers are acknowledged, the sender can infer that the earlier packet has been lost, and this allows QUIC to detect the packet lost without waiting for the long timeouts. Additionally, QUIC uses time-based detection also, where if a packet remains unacknowledged for a certain duration, it is also considered as lost. And these two mechanisms, they work together to provide faster and more accurate loss detection compared to traditional approaches, and this ensures that the lost packets are detected quickly, which improves the overall reliability and performance of this protocol that we are using. So here in Wireshark, we can kind of verify if there has been a loss. We can like do the loss detection here. And here I am selecting a packet that contains an ACK frame, and we can go with this packet number 3, which is an initial packet. And if we open it and expand the quick header, quick section, and open the ACK frame here particularly, and we can observe the acknowledgement details here. In particular, we can see the largest acknowledgement field, which is here, this, and it is written here as 3. And it represents the highest packet number that has been successfully received by the peer. And for example, if we say if the largest acknowledged number is 5 and it indicates that the packet 5 has been received and here it is 3, it means that 3 packets of this initial has been received by the destination, and at the starting we saw that we had 3 initial packets. So QUIC uses this acknowledgement based mechanism to detect packet loss without relying on the long timeouts. Additionally, QUIC also supplies time based detection also, where the packets that remain unacknowledged for a certain duration are considered as lost, and this demonstrates how QUIC detects packet loss efficiently using the acknowledgement based and the time based mechanisms. So now we will look at PTO and persistent congestion. PTO stands for prop timeout. And the top part of this diagram, it shows the prop timeout mechanism in QUIC. When a sender transmits a packet, a PTO timer starts. And if an acknowledgement is received, then the timer will be cancelled and everything will be okay. If an acknowledgement is not received, the PTO timer expires and the sender transmits one or more, it could be one or two prop packets, and each time PTO fires, the time or duration increases, which helps avoid excessive network load. This allows QUIC to recover from the potential loss without immediately reducing the congestion window. And then in the part 2, we have persistent congestion. The second part of the diagram, it shows the persistent congestion, which represents a more severe network condition. Persistent congestion is declared when multiple packets are lost over a period of time that exceeds a defined threshold. And this threshold is calculated using the smoothed round trip time, its variation, and acknowledgement delay. When persistent congestion is deleted, QUIC reduces the congestion window to its minimum value and it restarts the slow start. And this ensures that QUIC adapts to the heavy network congestion while maintaining the stability. Although the PTO and the persistent congestion are not explicitly labeled in Wireshark, we can infer them from the packet timing and the retransmission behavior. Here we can observe the gaps between the packet retransmissions followed by the new packets being sent from the timer that is given here. And this indicates that the sender waited for an acknowledgement and the retransmitted or sent prop packets when none was received. If such behavior continues over a longer duration, it may indicate the persistent congestion in the network is occurring. And this demonstrates how QUIC uses prop timeout for efficient recovery and persistent congestion detection to adapt to severe network conditions. Now let's observe how QUIC is being used in the real-world applications using the Chrome Developers tool. We already used the Wireshark. Now let's test it with this on the application layer particularly. Here I have opened the network tab and enabled the protocol column to view the protocols for each and every request, and let's reload the page again and see if we can get the H3. Yeah. So H3 here represents the HTTP version 3, and since HTTP version 3 is built on top of QUIC, that confirms that QUIC is being used for these requests. If we open an individual packet of HTTP3 protocol which runs over QUIC instead of TCP. However, unlike Wireshark Chrome Developers tool, it does not show low-level QUIC details such as the packet numbers or connection IDs as I already told, as it works on the application layer. This is because it works on the application layer. Therefore, QUIC can only be observed indirectly here through HTTP3 traffic. This demonstrates that QUIC is actively used in the modern web communication even though its internal packet level details are abstracted away at the browser level. While Wireshark it provides the packet level visibility, Chrome Developers tool, it confirms that QUIC's real-world deployment is through HTTP3